In this training, we'll go into more detail on spatial reuse, preamble puncturing, and target wake time in the new 802.11ax standard. We will begin with spatial reuse, which in 802.11ax, it is a feature called BSS Coloring, providing an identifier that is attached to each PHY header to indicate what wireless LAN it came from. Its purpose is to increase capacity in the dense environment with an increase of frequency reuse between basic service sets or those sharing the same SSID. Legacy high-density Wi-Fi deployments typically have multiple access points assigned to the same transmission channels due to limited amount of spectrum, which is an inefficient paradigm that contributes to network congestion and slowdowns. In addition, legacy IEEE 802.11 devices are unable to effectively communicate and negotiate with each other to maximize channel resources. 802.11ax or Wi-Fi 6 access points are designed to optimize the efficient reuse of spectrum in dense deployment scenarios using a range of techniques including BSS coloring. Basic Service Set Color is a 6-bit identifier that is attached to each PHY header to indicate what wireless LAN it is transmitted from. In high-density venues, such as stadiums or large conference rooms, this problem becomes more acute because of the number of APs and clients. Unnecessary medium contention is referred to overlapping basic service set or OBSS, also commonly referred to as co-channel interference. 802.11ax was tasked with the addressing of the OBSS challenge by improving spatial reuse, which often is referred to as BSS coloring. This mechanism, originally introduced in 802.11ah, known as spectralization, was published in 2017 and was to address the medium contention overhead due to OBSS. 802.11ax assigns a different color or a number between 0 and 63, which is added to the PHY header of the 802.11ax frame to each BSS in the environment. With BSS Color, an AP can identify the frames which are coming from other networks and ignore them as long as they are below a threshold of weakness to cut down on the need of deferring transmission due to outside interference and avoid unnecessary slowdowns. An analogy to describe spatial reuse using BSS coloring would be such as a school, where we have a rule that only one person talks at a time in a classroom to maintain order. If one student started talking, all the other students would stay silent. This is half-duplex communication is what Wi-Fi does. Only one person, or client or AP, talks at a time. In the real world, each client is doing a random backoff to see who gets to talk, and at times there are collisions and everyone must start over. If someone in a next-door classroom talks, we don't feel that we need to be silent. We may hear some muffled sounds, but the audio from the adjacent classrooms are low and don't cause interference. However, access points do not differentiate. In 802.11 standards, tell the APs that if you hear talking on the same channel, you stay quiet. An AP in a classroom may pick up low-level signal coming from adjacent classroom on the same channel and must stay quiet. So, applying the analogy, we must give the AP a means to figure out whether the person is talking inside the classroom or in another classroom in the school. That's where the concept of BSS coloring comes in. Shown here are two APs operating in a building. Both are on channel 36 and are in the same BSS or SSID. One is in one classroom and the other AP is in the classroom down the hall. I'll assign the AP on the right the color of red and the AP in the other classroom down the hall orange. Every client that is associated with the red AP also gets the color red. In our previous analogy, this is like saying every student sitting in classroom is red student. The other classroom is orange students. Before you speak, you must tell your color, essentially what classroom you're in. And before someone talks, they listen to see if anyone else is talking. If you're in the red classroom and another red client is talking, you stay quiet. If you hear someone but the color is orange, I know they are far away. Essentially, I will begin transmission over the detected signal. Our example, the spatial reuse channel access rules are: Is transmission detected? If yes, you ask if it's the same color, meaning you are in the same BSS. If yes, you treat the medium as busy and the frame is considered an intra-BSS transmission and the listening radio will defer transmission. This is how today's networks behave. If the color is different, then the frame is considered an inter-BSS transmission from the overlapping BSS service set. And the listening radio treats the medium as busy only for the time it took to determine the color bit was different. Next, you ask if the RSSI signal is greater than the alternate signal detected. If yes, then you treat the medium as busy and defer transmission. If no, this means the signal is weak and you can ignore the frame and start transmitting. Since both APs are on the same channel, this technology improves spatial reuse efficiency and performance. Let's show this in a different perspective. How do we deal with overlapping BSS and dense deployments? The current method is to defer. Today, we typically drop everything down to 20 MHz to minimize reuse. This caps our network capacity to 20 MHz BSS SSIDs. If you multiply that by your maximum data rate, you configure your maximum capacity. How do we increase the capacity? If you go to 40 or 80 megahertz and you're using 5 gigahertz to drop down to 4 or 5 channels, this gives you a 4 times increase in your network capacity from raw spectrum calculations. But in a dense environment, you'll be blocked by all these small BSS sizes. You will hear all these other transmissions, so you're going to defer for all of them. In the best case, you'll just be back to the 20 megahertz capacity because you're using less spectrum, allowing for increased channel options. In the worst case, you'll have collisions between all co-channel and co-frequencies in the BSS, and you can end up worse than if you were just using 20 megahertz. That's why designers for stadiums or large conference rooms typically pick a smaller bandwidth to minimize reuse. So how do we address this? In 802.11ah, they were trying to figure out how to manage a co-channel interference differently than the typical deferral. 802.11ah introduced a scheme called BSS Coloring, so you can assign a different color identifier to BSS and distinguish between co-channel BSS interference. There are 64 levels of color using bits 0 through 7, and frames from neighboring BSS or SSIDs can be treated differently when assessing channel availability. In this section, we'll look at preamble puncturing and how it improves spectrum efficiency. Preamble puncturing is an optional capability feature available whenever a 802.11ax AP detects a nearby AP on one of the 20 MHz channels used for its 80 MHz transmission. In the past, the AP can either use dynamic channel widths and shrink to 20 MHz transmission, or back off and wait, which leads to waste of spectrum. However, with 802.11ax, it can transmit across the 80 MHz channel except on the channel in use by the other AP. This utilizes the remaining secondary channels within the 80 MHz, maximizing the spectrum. This is known as preamble puncturing or non-contiguous channel bonding. Because it is considered an optional capability, we will see how this is adopted in production environments, but seems it could be effective in home or areas where wide transmission is in use. This feature is also available for 160 MHz channels. However, for this to work for either 80 or 160 MHz transmissions, it must be supported on both AP and client, and only secondary channels can be punctured. Another key feature that 802.11ax brings for battery-operated clients and mobile devices is improving on the existing 11AC power-saving mode. The new 11ax feature is called Target Waketime, or TWT for short. The way 802.11 Power Save works today is like an entire house having one large alarm clock. Even if only one person needs to be awakened, the others, when the alarm clock goes off, wakes up. The people who didn't have to wake up go back to sleep, and just one person gets up and goes to work. In the pre-11ax Wi-Fi world, this is what 802.11 Power Save does with its beacons. Everyone must listen to the beacons and see if the beacon is for them. This is our one house alarm clock. It means that mobile battery-operated clients, especially small IoT devices, are wasting precious battery time because they're being awakened frequently. 802.11ax is giving one alarm clock to each client. It is a programmable function depending on your traffic pattern. Target wake time enables the device to determine when and how frequently they will wake up to send and receive data. Essentially, this allows 11ax APs to effectively increase device sleep time and significantly conserve battery life, allowing such device like IoT to possibly sleep for hours without dropping their association. In addition to power saving on the client-side device, Target Wake Time enables wireless access points and devices to negotiate and define specific times to access the medium. APs can further protect these deep sleep devices by clearing the channel at the time of scheduled wake time to avoid back-off collisions or retransmits. This helps optimize spectral efficiency by reducing contention and overlap between users. The target wake time mechanism first appeared in 11AH in 2017. The power saving standard is specifically designed to support a large-scale deployment of IoT infrastructure devices, such as stations and sensors, that intelligently coordinate signal sharing. The TWD feature further evolved with the 11AX standard, as stations and sensors are now only required to wake and communicate with the specific beacons transmitting instructions for the TWT broadcast sessions they belong to. This allows the wireless 11AX standard to optimize power saving for many devices with more reliable, deterministic LTE-like performance. Another feature of the 11AX is that it supports 20 MHz only clients. 11AC required 80 MHz capable clients. 802.11ax supports 20 MHz only clients because the 11ax draft amendment was written with IoT devices in mind, as the devices are low cost, use little power, and have very small batteries. Using management frames, client stations will be able to inform a 11ax AP that they are operating as a 20 MHz only client. A 20 MHz only device can transmit and receive in either 2.4 or 5 GHz band. Examples of IoT devices are BLE or Zigbee sensors, medical devices, thermostats, and so forth. They do not require high bandwidth operations. 802.11ax has a protocol where the 20 MHz only devices only communicate on the primary 20 MHz channels. I'm showing a 40 MHz channel here, but it could be extended to 80 or 160 MHz. All 20 MHz packet exchanges of these clients are in the primary 20 MHz channel. You can have packet exchange of normal clients in the upper secondary and then have further mix and match having some normal clients in your primary as well as 20 MHz only clients, so it's very flexible. The key is that the 20 MHz only devices only operate in the 20 MHz channels. So in summary, spatial reuse can be accomplished in the 802.11ax by the use of BSS coloring. Spatial streams can be used more efficiently when 11ax APs can avoid occupied bandwidth and proceed with their transmission using preamble puncturing. IoT devices can increase their battery life by negotiating a target wake time, allowing them to sleep longer between transmissions.